Good afternoon, and thank you for joining this Tech Talks. Today, I'm going to present on a structured methodology for repurposing of pipelines for CCUS service. So why repurpose offshore pipelines for CCUS? Well, first of all, it's a project enabler, especially if the pipeline is connected to depleted gas reservoirs. We would reduce the capex potentially up to £2 million per kilometre by not installing a new pipeline. We would see reduced environmental impacts, not only from saving in producing new steel and concrete coating, but avoidance of infrastructure in environmentally sensitive zones. We would see reduced project lead times, and would meet the required stewardship expectations of the North Sea Transition Authority. So what's the potential for repurposing? Well, the Restream project reported on repurposing in Europe in 2021, looked at the potential for repurposing of oil and gas infrastructure for hydrogen and CCS, and they looked at both onshore and offshore pipelines, and they found that 70% of the existing offshore pipeline length may be suitable for CO2 transport. So there's a significant length of offshore pipelines that could potentially be reused. So what are the repurposing challenges? And when we think about the challenges, we need to consider that the CO2 stream may also include a number of impurities, so that includes water, nitrogen, hydrogen, and then some additional impurities such as hydrogen sulfide, oxygen, NOx and SOx, etc. And these impurities can both affect the phase envelope of the CO2, but also increase the severity of the potential corrosion of this due to the CO2. So the challenges we need to think of are, first of all, does the pipeline have sufficient capacity for CO2 transportation? Now, we're not going to say too much about this afternoon, but for some of the larger CCS schemes we're now looking at, we would expect to require a pipeline diameter of around about 20 inches or greater. Next, is the pipeline pressure rating suitable for dense phase CO2 operation? If we look at the phase envelope on the right-hand side, and we look at particularly the green envelope, which is for a 96% CO2 mix, we can see that the critical point is around 80 bar. So we're going to need a pipeline pressure somewhat in excess of that to allow for hydraulic losses along the length of the pipeline and potential reservoir repressurization during the lifetime of the CCS scheme. Next is the current condition of the pipeline known. The pipeline may have been in hydrocarbon service for a number of decades, so may have suffered corrosion and other degradation. Then, are the original pipeline materials and design suitable for repurposing? Does the pipeline comply with contemporary design codes? And does the pipeline have sufficient remaining life? So to address these challenges, we've developed a structured roadmap. So the roadmap shows a number of swim lanes, each of which corresponds to one of the challenges. And the roadmap shows the steps we have to go through to address each challenge. The roadmap also shows the interaction between the challenges and the tasks we need to undertake. So to illustrate the roadmap within this presentation, we're going to consider 5 aspects. First of all, we'll look at material suitability. We'll look at current condition and inspection requirements. We'll look at CO2 propagation fracture control. We'll look at requalification to contemporary design codes. And finally, we'll look at life extension. So first of all, material suitability. And here we need to consider parent line pipe, welds, and any other fittings that may be present in the pipeline. So we start off by considering what are the desirable properties for dense phase CO2 transportation. So typically we would like low carbon equivalent, would like good ductility, avoidance of high yield to tensile ratios, good fracture toughness, um, avoidance of high hardness, sour service rating, because we're going to be likely to have hydrogen sulfide in the CO2 stream. We'd like to have control of inherent defects and good levels of inspection to demonstrate that we have low levels of inherent defects. So to demonstrate confirmation of those properties, we need to review the original line pipe and welding specifications. We need to review the manufacturing data books and the weld procedure qualification records. And from those records, we can extract the relevant properties of the pipeline. So on the right-hand plot, from a large number of we're showing the results of a large number of Sharpie impact testing for a long pipeline. And as we'll see later, Sharpie impact energy is an important property for a CO2 pipeline. And finally, we then need to identify if there's any gaps in the data set and then identify any mitigations. So for example, we may need to do some further testing on any spare or recovered line pipe, or if we still have some data gaps, we may need to tighten up on the specification of impurities for the CO2 fluid. Next, we need to consider the current condition of the pipeline and inspection requirements. So we can start off by considering what historical corrosion or damage may have occurred under the previous hydrocarbon service. So that may be general corrosion loss, pitting, cracking, etc. We can then review historical inspections, whether they be ILI, what type of ILI was performed, and how effective that would have been at detecting the degradation methods. If we have a population of known defects from those inspections, we can determine the safe working pressure using industry methods such as ASME B31G and DNV RPF 101. Once we've done that, we need to think about how future CO2 service may affect those existing damage that we may have in the pipeline, and how it may how those defects and degradation may develop in future. And once we've done that, we can identify any requirements for confirmatory inspections, and that may well be further ILI runs, and we can also think about what type of ILI techniques would be most appropriate to identify the defects we're particularly interested in. Next, we'll consider propagation fracture or running ductile fracture control. Now, running ductile fracture is an issue for natural gas pipelines, but it's a more severe issue for dense phase CO2 pipelines. And the reason for this is that if we suffer a local loss of containment or rupture of a CO2 pipeline and the CO2 starts to decompress, it has an unusual decompression behavior. First of all, we have a rapid decompression through the dense phase region, but as we hit the liquid gas line in the phase envelope, we see these long plateaus in the decompression curve, and it's these long plateaus which drive the ductile fracture, the running fractures, and the plateau pressure we call the saturation pressure, And the plot on the right-hand side shows we've plotted 3 lines here for increasing levels of impurities, and then 3 further lines for the same levels of impurities, but at a higher pressure of 35 degrees. And you can see that both increasing impurities and increasing in temperature increase the saturation pressure, and hence the severity of the tendency for fracture propagation. Now, resistance to fracture propagation, which is driven by the properties of the pipeline, in particular its wall thickness, its grade and toughness, and we call that the arrest pressure. So propagation fracture is halted when the arrest pressure exceeds the saturation pressure. So we have 2 methods which we can use to assess fracture. The first method is BS ISO 27913, and it uses the established Battelle 2-curve model for natural gas, but with correction factors for CO2. But it's not fully calibrated, and it may be non-conservative for CO2. So to illustrate the method, on the left-hand plot, this is for a 24-inch pipeline. So we've plotted required Sharpie impact energy against wall thickness, and we've done that for 3 increasing levels of saturation pressure. So for the lowest saturation pressure of 60 bar, if the pipeline had a wall thickness of 18 millimeters, you can see the required Sharpie energy is 80 joules. But for increasing saturation pressures, the required impact energy can increase rapidly, and in this case, at 75 bar, we need a saturation impact energy of around 160 joules. Now, the right-hand plot shows an empirical design method developed by the CO2 Safe Arrest JIP and recently implemented in DNV RPF 104. So the design method plots a non-dimensionalized saturation pressure against a non-dimensionalized arrest pressure. So if we take our 3 points from the left-hand plot and transpose them onto the right-hand plot, they fall here. So you can see the lower 2 saturation pressures fall in the area called evaluation based on special assessments, but the higher saturation pressure falls into the zone called propagation expected. Now, if our pipeline had achieved a higher Sharpie energy, the 3 points here would transpose over to these 3 points here in this vertical line, and then the evaluation would be based on small scale testing. So we would be in a better place in terms of being able to resist propagation fracture. So this is an ongoing area of research, and the industry methodology is not yet mature, and we may require project-specific testing. Next, we'll look at requalification to contemporary codes. So on this slide, we've showed the evolution of design codes for offshore pipelines. So in terms of the UK, most offshore pipelines prior to 1993 were designed to IP6. In 1993, there was a big change when BS 8010 was introduced. And then in 2004, the code evolved to become PD 8010. And there's been periodic updates of the code up to today. In terms of international design codes, and particularly DNV, the submarine design code was first introduced in 1976. There was a major update in 1981, and then a further update in 1996 to DNV 96. And the code then became OSF 101 in 2000, subsequently was rebadged as STF 101 and has again gone through periodic updates. So when we're thinking about requalification to contemporary codes, we need to think about the pipeline design, we need to think about material requirements, welding requirements, inspection requirements, which are all part of the overall design code. Now, if our pipeline had been designed prior to 1993, it's not so easy to map the clauses, design code clauses which existed at that time to modern design codes. So it may be more pragmatic to first to consider the key threats that apply to the pipeline in its future service, and then to consider whether the pipeline can meet the requirements of the latest code. For pipelines designed post 1993, the task is a little more straightforward because it's generally more easy to map the specific clauses from the original design code to the new code, to the latest design codes. There is also further guidance on design of CO2 pipelines given in BS ISO 27913 and DNV RP F104. So we can take advantage of that guidance to help us with the requalification of the pipeline. So finally, in terms of life extension, there are established risk-based processes for pipeline life extension given in ISO and NORSOC codes. When we're thinking about life extension, we should focus on time-dependent degradations such as fatigue and corrosion. So the methodologies we use for life extension, or the approach we use, is we have a threat matrix of these time-dependent degradation mechanisms, and we consider what are the risks today, and then we can consider what are future risks. And if those future risks have become too high, we can develop further mitigations, for example, more inspection to reduce those risks to an acceptable level. So what we need to do when we're considering a dense phase CO2 is just make sure that the specific or additional threats that are associated with the dense phase CO2 are incorporated in our threat matrix, and then we can use the existing frameworks to successfully undertake life extension. So in summary, there are a number of challenges for repurposing pipelines for CO2 service, but there are a number of significant benefits in terms of enabling projects, reducing capex, environmental impacts, and project lead time. So we believe that we can achieve these benefits by the use of a structured approach to demonstrate safe repurposing of pipelines for CCUS. Thank you for listening to this Tech Talks. If you have any queries, please don't hesitate to get in contact with myself, and would be delighted to respond. Thank you again.